Welcome to the channel. I'm glad you're here. In this video, I want to take a slow walk through a question that sounds simple at first, but keeps unfolding the longer you sit with it. When conditions change, what survives? What keeps its shape, keeps its identity, keeps functioning, or simply keeps existing while other things break apart, dissolve, or disappear? It's natural to answer that question with stories. We reach for intention. We imagine strategy. We picture a system trying to endure, wanting to adapt, learning how to survive. Those stories make sense in human life because we do plan. We do choose. We do adjust our behavior in response to changing circumstances. But the universe does not plan. It does not anticipate. It does not look ahead and decide what it will need later. Stars do not strategize their fuel use. Galaxies do not aim to remain stable. Atoms do not negotiate their bonds. Even life, when you strip away the language we naturally project onto it, is not a global intention marching forward. It is a local outcome that persists when conditions permit it and vanishes when conditions do not. So in this pillar, I want to hold on to a framing that's quiet but powerful. Survival is not a goal. Survival is what remains. That is not a poetic claim. It is a structural one. When an environment changes, it creates pressures. Those pressures are not moral, and they are not personal. They are simply constraints: temperature, density, radiation, chemistry, gravity, scarcity, noise, drift, and time. Anything that cannot stay coherent under those constraints tends to break down. Anything that can stay coherent tends to remain. If the conditions keep changing, the filter keeps running, and what survives in the long view begins to look like it was chosen. But the choice is an illusion. It's a consequence of elimination. That is one of the central themes of this video. Selection without purpose. A filter without a chooser. You can see this everywhere once you start looking for it. In materials science, a structure might be strong under steady load, but fail catastrophically when the load changes direction. In chemistry, one arrangement of atoms may be stable for billions of years while another falls apart in microseconds, not because one is more meaningful than the other, but because the energy landscape makes one basin deep and the other shallow. In astronomy, a planetary system might remain stable for eons, then become chaotic after a small perturbation, because stability was conditional, not guaranteed. In cosmology, a phase of the universe might favor structure formation for a time, then slowly suppress it as expansion and entropy flatten the gradients that once made complexity easy. The universe is full of survivors that did not earn survival. They simply fit the constraints that happen to exist. That sentence can feel cold if you read it as a statement about value, but it is not about value. It is about mechanism. The universe is not evaluating worth. It is applying conditions, and conditions don't care what we hoped would last. This is also why the question, what survives, is inseparable from another question, what changes? Because the filter only matters when conditions move. If the environment is perfectly stable forever, almost anything that is stable under that one set of conditions will persist. But if conditions shift, slowly or suddenly, gently or violently, then persistence becomes selective. The environment stops being a background and becomes an active sculptor. You already know this intuitively from ordinary life. A bridge can last 100 years in a mild climate and fail quickly in salt air. A species can thrive until the temperature shifts a few degrees. A technology can dominate until the underlying infrastructure changes. In each case, it is not the object alone that determines its fate. It is the match between the object and the conditions around it. In physics terms, survival is relational. It is not an intrinsic badge. It is an ongoing negotiation with the environment. even for things that are not alive and cannot negotiate in any conscious sense. A crystal survives because its internal ordering is energetically favorable under local conditions. A star survives because hydrostatic equilibrium balances inward gravity and outward pressure for a long time. A galaxy survives because it sits in a stable gravitational configuration and avoids disruptive interactions for long enough. And when conditions change enough, those survivals end, not as punishments, but as transitions. A star leaves the main sequence because its fuel state changes. A material fractures because stress exceeds toughness. A planetary orbit destabilizes because resonances accumulate. A stable arrangement becomes metastable, and metastability is always temporary when the world keeps moving. One of the reasons I'm making this pillar is that survival is often described in a way that hides these mechanics. We talk as if survival is about strength, or we talk as if it's about intelligence, or we talk as if it's about being specially favored by the universe. But in many domains, the opposite is true. Sometimes strength is the problem. Sometimes rigidity is fragility in disguise. Sometimes the systems that last are not the ones that are maximally optimized for one condition, but the ones that carry slack. Redundancy, flexibility, diversity, tolerance, so that when conditions shift, they don't shatter. This video will move slowly through that contrast, rigidity versus adaptability, not as a moral lesson, but as a physical pattern. Rigidity can be beautiful. In the right environment, rigidity is stability. It gives you precision. It gives you predictability. It gives you long-lived structure that holds its shape against noise. But rigidity also comes with a price. It narrows the range of conditions under which the system can remain coherent. When the world changes outside that range, the rigid system has no way to deform gracefully. It fails suddenly. Adaptability looks messy by comparison. It is harder to describe. It often appears inefficient. It carries extra degrees of freedom. It tolerates variation. It sacrifices perfect performance for broader performance. But adaptability is often what allows endurance across unknown futures. It does not require foresight. It simply avoids being too brittle. In later sections, we'll look at these ideas across multiple scales because the pattern repeats. It shows up in how stars end. It shows up in how galaxies isolate. It shows up in the kinds of molecules that survive radiation. It shows up in the architectures that allow error correction. It shows up in life, but it is not limited to life. It is a general story about what remains when conditions apply pressure. And I want to set one expectation early, because it matters for the tone of this channel. This is not a video about winners. It's not a video about superiority. It's not a celebration of selection as if it were a moral force. It's an attempt to see the universe more clearly by removing intention where intention does not exist. When we do that, something interesting happens. The universe becomes less theatrical, but more coherent. We stop asking why it chose certain outcomes, and we start asking which constraints were operating, which patterns were robust, and which structures were fragile. That shift also has a surprising emotional effect. It can make the universe feel calmer, because if the universe is not judging, then persistence is not a prize, and failure is not a disgrace. Things simply happen within conditions. Structures arise, endure for a time, and dissolve. That is not a tragedy written into the fabric of reality. It is the natural behavior of systems in time, and there's another reason to hold this framing. It keeps us honest about what we know. When we say this survives, we are really saying, under these conditions, this is stable. That is a claim we can test. It is also a claim we can revise. As we learn more, we can refine which conditions matter, which mechanisms dominate, and which patterns are more robust than we thought. This pillar is part of a longer series exploring how structure, information, and persistence shape the universe, from cosmology and physics to complexity and emergence, with an emphasis on staying grounded in what we can actually justify. Some of the language I use will feel philosophical, but the goal is not philosophy for its own sake. The goal is clarity, to describe what physics already implies, slowly enough that the intuition has time to catch up. So here's the question I want to leave hanging in the air as we begin. If the universe does not aim and does not plan and does not choose, then why do certain things last? What is the price of endurance? And what does it reveal about the deep structure of reality that the same kinds of persistence patterns appear in stars, in chemistry, in galaxies, and in any system that must survive changing conditions? That's where we're going. In the next section, we'll start with the most foundational piece, selection without purpose. We'll talk about what a filter is in physical terms, why elimination creates the illusion of choice, and why persistence can be understood as what remains when constraints do their quiet work. My name is Charles Carroll. Thanks for being here, and thanks for taking the time to move slowly through this with me. Section 2, Selection Without Purpose. When people hear the word selection, they almost always imagine a chooser, something deciding, something preferring one outcome over another. Even when we talk about natural selection, we tend to smuggle intention back in through the language. We say organisms adapt, systems optimize, structures are favored, outcomes are selected for. Those phrases are useful shorthand, but they hide what is really happening. In physics, selection does not require a selector. What we are actually describing is elimination under constraint. Certain configurations cannot persist under given conditions, so they disappear. Others happen to be compatible with those conditions, so they remain. Over time, the remaining set begins to look special, as if it were chosen, when in reality it is simply what has not yet failed. This distinction matters deeply because once you remove purpose from the process, the universe starts to make more sense. Let's slow this down. Imagine a landscape of possibilities, not a literal landscape, but a space of configurations, arrangements of matter, energy, fields, or relationships. Some of those configurations are stable, some are unstable, some are stable only under very specific conditions. Some are robust across wide ranges of temperature, pressure, radiation, or disturbance. Now introduce time. Time is not a passive backdrop here. Time allows conditions to change. It allows fluctuations to accumulate. It allows small instabilities to grow. And it allows fragile configurations to be tested repeatedly over and over until they break. In that setting, selection is not something that happens once. It is continuous. At every moment, the environment is asking a quiet question of every structure that exists. Can you remain coherent under these conditions? Most configurations cannot. They fall apart quickly. They dissolve. They decohere. They react, decay, fragment, or thermalize. Their disappearance does not require an event. It is simply the default outcome when stability is absent. What survives are the exceptions, configurations that sit in regions of configuration space where small disturbances do not immediately lead to collapse. In physics, we often describe these regions as basins of attraction or stable equilibria. If a system is nudged slightly, it returns. If it is perturbed moderately, it deforms but does not break. Only when a threshold is crossed does it transition into something else. That is not selection with intent. That is selection by structure. You can see this even in the simplest physical systems. A ball placed at the bottom of a bowl will return to the center if nudged. A ball balanced on a peak will fall off with the slightest disturbance. The bowl does not prefer the ball at the bottom. It does not choose that outcome. The geometry of the system makes one configuration stable and the other unstable. Over time, only the stable configuration persists. Scale this up, and you have the same logic operating everywhere in the universe. Atoms persist because certain electron configurations are stable under electromagnetic forces. Molecules persist because certain bond arrangements minimize energy under given conditions. Crystals persist because periodic arrangements lower free energy. Stars persist because hydrostatic equilibrium balances competing forces. Galaxies persist because gravitational orbits settle into long-lived patterns. None of these systems are trying to survive. They simply exist in configurations that are compatible with the forces acting on them. This is what selection without purpose really means. The universe does not search for good solutions, it eliminates bad ones. That framing is subtle but powerful. It flips the story from one of optimization to one of filtering. And filtering is always cheaper than optimization. Filtering does not require foresight. It does not require evaluation of alternatives. It only requires that some configurations fail faster than others. Once you see that, a lot of confusion dissolves. People often ask, why does the universe produce structure at all? The implicit assumption is that structure must be generated by some guiding principle. But structure does not need to be generated intentionally if unstructured configurations are unstable. If chaos decays quickly and order decays slowly, then order accumulates without anyone aiming for it. This is not a violation of entropy. It is a consequence of how entropy operates locally. Entropy increases globally, but local pockets of lower entropy can persist when they are supported by flows, constraints, or energy gradients. Those pockets are not miracles. They are temporary refuges where certain patterns can endure, and as long as they endure, they shape what comes next. This is another key idea. Persistence is not passive. A structure that remains becomes part of the environment for everything that follows. A surviving star influences nearby matter. A surviving molecule participates in further chemistry. A surviving galaxy defines a gravitational field. Even a surviving vacuum state constrains what kinds of excitations are possible. So selection without purpose does not just eliminate, it sculpts. But the sculpting happens backward in time, not forward. The environment does not anticipate what will be needed. It simply removes what cannot cope. The remaining structures then bias future possibilities, not because they were chosen, but because they are there. This is why selection often looks directional in hindsight. We look at what exists now and trace a path backward, seeing a sequence of survivals. But that path is not a plan, it is a record. Another way to say this is that selection creates memory without intention. The present state of the universe encodes which configurations were stable enough to last. That encoding is physical, not symbolic. It lives in matter, fields, distributions, and correlations. The universe remembers what worked only because what did not work is gone. This is an uncomfortable idea for humans, because we are used to memory being deliberate. We remember because we care. The universe remembers because elimination is irreversible. Once a configuration collapses into a simpler state, the detailed path that led there is often lost. That loss is entropy. The surviving configurations carry less information about the alternatives that failed. Over time, the universe's state becomes a compressed record of what endured. This also explains why selection often looks conservative. Systems that survive tend to reuse the same patterns again and again. Stable atomic structures recur everywhere. Stable orbital mechanics repeat across galaxies. Stable forms of energy flow reappear at different scales. This repetition is not laziness. It is inevitability. When the space of possibilities is filtered by stability, the same attractors show up repeatedly. This brings us to an important correction. Selection without purpose does not mean anything can happen. In fact, it means the opposite. Most things cannot happen for very long. The universe is extremely selective, not because it chooses carefully, but because it eliminates relentlessly. The space of all possible configurations is enormous. The space of configurations that can persist under realistic conditions is tiny. That is why the universe looks ordered instead of arbitrary. Order is not imposed. It is what remains. Once you internalize this, a lot of anthropocentric confusion fades. We stop asking why the universe allows certain things and not others. We stop treating survival as a reward. We start seeing persistence as compatibility, and compatibility has nothing to do with meaning. This is especially important when we later talk about life, intelligence, or technology. Those topics invite purpose-heavy language, but the same filtering logic applies. Life persists where chemistry, energy flow, and stability allow it. Intelligence persists where information processing can be maintained. Technology persists where materials, energy, and environment support it. None of these outcomes are guaranteed. None are intended. They are conditional. And when conditions change, persistence can end. This brings us back to the core question of this pillar. What survives when conditions change? Selection without purpose is the first part of the answer. What survives is not what is best in any absolute sense. It is what remains compatible as the environment shifts. Sometimes that favors rigidity. Sometimes it favors adaptability. Sometimes it favors simplicity. Sometimes it favors redundancy. There is no universal strategy because there is no universal environment. The universe is not optimizing for anything. It is filtering continuously. In the next section, we will look at one side of this contrast in detail, rigidity. We'll explore why rigid systems can be extraordinarily stable for long periods, why they often dominate when conditions are steady, and why that same rigidity can turn into sudden fragility when conditions cross a threshold. Proceeding slowly, we'll see that endurance always has a cost, and that cost depends on how tightly a system is tuned to its world. Section 3. Rigidity. When strength becomes fragility. Rigidity is often mistaken for resilience. When we see a system that holds its shape, resists disturbance, and behaves predictably over long periods of time, it is natural to describe it as strong. We admire structures that do not bend, rules that do not waver, patterns that do not drift. In everyday language, rigidity feels like reliability. If something is rigid, we expect it to endure, and for a while, that expectation is often correct. Rigid systems can be extraordinarily stable under the conditions they were shaped by. They can last for immense spans of time. They can dominate their environments. They can appear almost timeless. But that stability is conditional. It is stability within a narrow envelope. And when the world moves outside that envelope, rigidity can turn from strength into fragility very quickly. To understand this, we need to be precise about what rigidity actually is. Rigidity is not just stiffness. It is not simply resistance to deformation. At a deeper level, rigidity means that a system has very few ways to respond to disturbance. Its internal degrees of freedom are constrained. Its behavior is tightly specified. When pushed, it either returns to its original state or fails. This can be enormously advantageous when conditions are steady. A rigid crystal lattice, for example, maintains its structure because the arrangement of atoms sits at a deep minimum in the energy landscape. Small thermal fluctuations do not disrupt it. The pattern snaps back into place. The same is true for many mechanical structures, orbital configurations, and even theoretical descriptions. Precision emerges from constraint. But that same lack of flexibility also means there are few alternative paths available when conditions change. Think of a glass rod. Under gentle forces, it behaves beautifully. It is stiff, transparent, and predictable. It can support loads without bending. But once the applied stress exceeds a certain threshold, the rod does not gradually adapt. It shatters. The transition from stability to failure is abrupt. That is the signature of rigidity. In physics, we often describe this in terms of phase transitions or tipping points. A system can appear perfectly stable right up until a critical parameter is crossed. Temperature, pressure, stress, radiation intensity, or environmental coupling changes just enough, and suddenly the old configuration is no longer viable. The system reorganizes, often violently, into something simpler. The important point is that the failure is not a surprise from the system's point of view. It is built into the structure. The system never had the capacity to respond smoothly to that kind of change. This is why rigid systems often give us a false sense of permanence, because as long as the environment stays within familiar bounds, nothing seems to threaten them. The failure modes are invisible until they are triggered. You can see this pattern across many scales. In astrophysics, a star can remain in a stable burning phase for billions of years. The balance between gravity and pressure is exquisitely precise, but that balance depends on fuel composition, mass, and energy transport. When the fuel state changes, the same rigidity that kept the star stable prevents it from adjusting gradually. The core contracts, reactions accelerate, and the system transitions rapidly into a new phase, sometimes gently, sometimes explosively. In planetary systems, orbital resonances can maintain stability for immense periods, but small perturbations can accumulate. When a resonance is broken, the system does not gently reconfigure. Orbits can become chaotic. Bodies can be ejected or collide. Stability gives way to sudden rearrangement. In material science, rigid structures often fail catastrophically rather than deform plastically. In contrast, materials that can bend, stretch, or redistribute stress may survive larger changes without breaking. The same logic applies to abstract systems as well. Highly optimized processes, whether mechanical, computational, or organizational, often perform extremely well under expected conditions. But that optimization removes slack. When unexpected conditions arise, there is no buffer. The system cannot absorb shock. It either works or it doesn't. This brings us to a crucial idea. Rigidity concentrates performance at the expense of adaptability. A rigid system is often optimized for a narrow slice of configuration space. Within that slice, it excels. Outside of it, it collapses. This is not a flaw in design. It is a trade-off imposed by constraint. In the universe, rigid structures persist not because they are universally robust, but because for long stretches of time, the conditions they require are met. During those stretches, they dominate. They shape their environments. They influence what else can exist nearby. Their presence can even suppress alternatives that might have been more adaptable but less efficient. This is why rigidity often correlates with apparent success in stable eras, but the universe does not guarantee stability forever. Conditions drift. Background parameters change. Gradients flatten. Noise accumulates. External interactions occur. Eventually, the environment moves far enough that the rigid system is no longer compatible. When that happens, the transition is not graceful. This is one reason why extinction events in stars, in planetary systems, in ecosystems, are often abrupt in the record. The system did not slowly fade. It crossed a boundary. This also helps explain why rigidity can look like foresight in hindsight. We look back and see a structure that lasted for a long time, and we imagine it was well adapted. But in many cases, it was simply well matched to conditions that happened to persist. The endurance was contingent, not strategic. There's another subtle cost of rigidity that is easy to miss. Rigid systems tend to be brittle to novelty. Because they are tightly constrained, they resist deviation. That resistance suppresses experimentation. In physical terms, fluctuations are damped quickly. Deviations are corrected. This maintains stability, but it also prevents the system from exploring nearby configurations that might be viable under slightly different conditions. As a result, rigid systems often dominate until they don't, and then they vanish without having produced successors that can handle the new environment. This is not a criticism, it is a description. The universe is full of rigid survivors that shaped entire eras. Stable nuclear reactions, stable chemical bonds, stable orbital dynamics, stable vacuum states. Each of these rigidities allowed structure to persist long enough for complexity to accumulate, but each also defines a limit. When conditions exceed that limit, the old structure cannot follow. Understanding rigidity this way helps dissolve a common misconception. We often imagine that what survives longest must be the most advanced or fit in some absolute sense. But longevity alone does not imply broad robustness. It often implies narrow excellence. Rigidity is a strategy the universe employs frequently because stable conditions can last a very long time. But it is not the only strategy, and it is not always the winning one when the world becomes unpredictable. In the next section, we will turn to the counterpoint, adaptability. We will explore systems that appear inefficient, redundant, or messy, yet endure precisely because they are not tightly tuned. We will see how slack, diversity, and redundancy, features that look wasteful from a rigid perspective, become powerful assets when conditions change. Section 4. Adaptability, the power of slack and redundancy. Adaptability often looks inefficient from the outside. When we compare a rigid system to an adaptable one, the rigid system usually appears cleaner, sharper, and more impressive. It does one thing extremely well. It wastes little energy. It behaves predictably. By contrast, adaptable systems often look messy. They contain redundancy. They tolerate variation. They allow fluctuations that seem unnecessary or even counterproductive. From a narrow performance perspective, adaptability can look like weakness. But in a changing universe, adaptability is often the reason anything lasts at all. To understand why, we need to revisit the idea that persistence is not free. Every structure that survives pays a cost. Rigid systems pay that cost by narrowing the range of conditions under which they can exist. Adaptable systems pay it by carrying slack, extra capacity, unused pathways, and degrees of freedom that are not strictly required for present conditions. That slack is not an accident, it is the price of flexibility. In physical terms, adaptability means that a system can respond to disturbance in more than one way. When pushed, it does not simply snap back or fail. It can deform, reconfigure, redistribute stress, or shift into a nearby configuration that is still viable. This ability to move within configuration space without collapsing is what allows adaptable systems to persist across environmental change. One of the clearest examples of this appears in materials that are ductile rather than brittle. A ductile material absorbs energy by deforming. Its internal structure allows bonds to stretch, slide, and rearrange without breaking outright. This deformation dissipates stress and prevents catastrophic failure. The material may no longer be perfectly shaped, but it remains intact. The same principle applies far beyond materials. In chemistry, adaptable molecular systems often involve networks of reactions rather than single pathways. If one reaction route is blocked, others can carry the process forward. This redundancy allows chemical systems to remain functional under fluctuating conditions of temperature, pressure, or concentration. Highly specific reactions may be efficient under ideal conditions, but they are fragile when those conditions drift. In astrophysics, adaptability appears in systems that are not maximally optimized for a single configuration. Consider stellar systems with a range of masses, compositions, and orbital arrangements. Diversity in initial conditions can allow some members of the system to survive disturbances that eliminate others. A system composed entirely of tightly tuned orbits may be more orderly, but it is also more vulnerable to resonance-driven instability. Adaptability is not about resisting change, it is about absorbing it. This distinction matters. Rigid systems fight change by opposing deviation. Adaptable systems accommodate change by redistributing it internally. They do not insist on returning to a single precise state. They allow multiple states to be acceptable. In dynamical systems language, adaptable systems occupy broader basins of attraction. They have multiple nearby stable configurations rather than a single deep minimum. Perturbations move the system within the basin rather than ejecting it entirely. This is why adaptability is so often linked to redundancy. Redundancy means that the system has more components or pathways than are strictly necessary for its immediate function. That extra capacity can seem wasteful in stable environments, but redundancy allows the system to continue functioning even when parts fail or conditions shift. In information theory and computation, redundancy is a well-known strategy for error correction. Bits are repeated. Signals are encoded across multiple channels. Noise corrupts some parts of the message, but the overall pattern can still be recovered. Without redundancy, a single error can destroy the entire signal. The universe uses this strategy extensively. Stable structures often persist not because every component is perfect, but because imperfections do not immediately cascade into failure. Noise is tolerated, fluctuations are absorbed, errors are corrected or isolated. This is closely related to another important concept: degeneracy. Degeneracy occurs when different internal configurations produce the same external behavior. In other words, the system can achieve its function in multiple ways. If one internal pathway is disrupted, another can take its place without changing the system's outward role. Degeneracy is distinct from redundancy, but they often work together. Redundancy duplicates components. Degeneracy allows variation among components. Together, they create robustness. From a rigid perspective, this looks inefficient. Why carry extra pathways you might never need? Why allow internal variation that complicates behavior? But in a world where conditions are uncertain, these features are not luxuries. They are insurance. Adaptability also tends to slow things down. Highly optimized rigid systems often operate at maximum efficiency and speed. They convert energy rapidly. They minimize delay. Adaptable systems, by contrast, often trade speed for stability. They respond more slowly. They buffer changes rather than amplifying them. They damp fluctuations instead of exploiting them. This slowness is not a defect. It is a stabilizing feature. Fast systems are more sensitive to noise. They amplify small deviations quickly. Slow systems average over fluctuations. They respond to trends rather than spikes. In an environment where conditions drift gradually, this averaging can be the difference between survival and collapse. This is one reason why long-lived structures in the universe often evolve slowly. Stars burn fuel at rates that balance longevity against luminosity. Galaxies evolve over billions of years. Chemical equilibria settle gradually. Rapid change is exciting, but it is also dangerous. Adaptability favors patience. There is also a deeper cost to adaptability that is easy to overlook. Adaptable systems are often less precise. Because they allow variation, they cannot guarantee exact outcomes. Their behavior may be noisy. Their performance may fluctuate. From the standpoint of rigid optimization, this looks like a loss. But precision is only valuable when the environment demands it. When conditions change unpredictably, flexibility can matter more than exactness. This brings us back to the central framing of this pillar. Persistence is a filter, not a goal. The universe does not reward adaptability because it values flexibility. Adaptable systems persist because they remain compatible across a wider range of conditions. This does not mean adaptability always wins. In stable environments, rigid systems can dominate for long periods. They can outcompete adaptable systems by being more efficient, more precise, or more ordered. But when the environment shifts, that dominance can vanish quickly. The universe alternates between eras where rigidity is favored and eras where adaptability is favored. Over very long timescales, systems that incorporate some degree of adaptability tend to persist across transitions, while purely rigid systems tend to be confined to specific epochs. This pattern repeats across scales because it reflects a fundamental trade-off. You can be perfectly tuned to the present, or you can be prepared for an unknown future. You cannot maximize both simultaneously. Adaptable systems accept imperfection in exchange for endurance. In the next section, we will examine the cost of endurance directly. We will look at what persistence requires in terms of energy, maintenance, simplicity, and sacrifice. We will see that nothing survives indefinitely without paying a price, and that different persistence strategies incur different costs. Section 5. The cost of endurance. Persistence always has a price. This is one of the most important corrections to make when thinking about survival across time. It is tempting to imagine that some structures endure simply because they are favored, lucky, or exceptionally well designed. But in physics, endurance is never free. Anything that remains coherent while conditions change must pay for that coherence in some way. The cost may be obvious or it may be subtle. It may be paid in energy, in simplicity, in flexibility, in speed, or in the range of possible futures that the system is willing to give up. But the cost is always there, because persistence means resisting decay, and resisting decay always requires trade-offs. To see this clearly, it helps to start with thermodynamics. The universe as a whole evolves toward higher entropy. Energy spreads, gradients flatten, differences dissolve. That tendency is not a preference. It is a statistical fact about how many more disordered states exist than ordered ones. Against that backdrop, any structure that remains ordered for a long time is doing something non-trivial. It is either sitting in a configuration that is extraordinarily stable, or it is actively exporting entropy to its surroundings, or both. A crystal is an example of cheap persistence. Once formed under the right conditions, it can remain ordered for extremely long times without ongoing energy input. The cost is paid up front. The crystal occupies a very specific region of configuration space, and it can only exist under limited conditions. Change the temperature or pressure enough, and the crystal melts, fractures, or transforms. Its persistence is passive but narrow. A star, by contrast, is an example of expensive persistence. It remains far from equilibrium by continuously burning fuel and radiating energy outward. The star exports entropy to its surroundings in order to maintain internal structure. The cost is ongoing and enormous. When the fuel runs out, the persistence strategy fails, and the star transitions into a different state. These two examples illustrate a key distinction. Some systems persist by being simple and deeply stable. Others persist by being active and continuously maintained. Both strategies work, but both impose limits. This brings us to a central idea. Endurance constrains future options. A system that pays the cost of persistence by narrowing its configuration space gives up flexibility. It cannot easily become something else. A crystal cannot suddenly reconfigure into a radically different structure without first losing its order. A rigid orbit cannot smoothly morph into a different orbital pattern without instability. A system that pays the cost of persistence through active maintenance gives up longevity. It burns resources. It consumes gradients. It relies on conditions that may not last. Its future is bounded by its fuel. In either case, persistence is a commitment. To remain what you are is to accept that you cannot become everything else. This is why endurance and adaptability are always in tension. An adaptable system carries slack so that it can respond to change, but that slack costs energy, complexity, or efficiency. A rigid system avoids those costs by specializing, but specialization reduces the range of survivable conditions. There is no free lunch here. We can see this trade-off very clearly in information-bearing systems. Any system that stores information must resist noise. Noise is entropy in action. Thermal fluctuations, radiation, and interactions all tend to scramble correlations. To preserve information, a system must either be physically isolated and stable, or it must continuously correct errors. Isolation is cheap but fragile. Error correction is robust but expensive. A hard drive stores information cheaply when kept in a stable environment. Expose it to heat, radiation, or mechanical stress, and the information degrades. A living cell, by contrast, stores information in DNA, but invests enormous energy into repair, replication, and proofreading. That energy cost allows the information to persist under conditions that would quickly destroy passive storage. Again, the cost of endurance shows up as a trade-off between energy expenditure and environmental tolerance. This pattern also appears in the persistence of physical laws as we describe them. Our most successful theories are often effective theories, descriptions that work within certain domains and break down outside them. Their endurance comes from their robustness across a range of scales, not from universal exactness. The cost is that they give up precision at extremes. Newtonian mechanics persists because it works extraordinarily well under everyday conditions. Its endurance as a useful description comes from its simplicity and broad applicability. But it gives up accuracy at relativistic speeds and quantum scales. More exact theories exist, but they are more complex and less convenient. Here, endurance is paid for in abstraction. We trade completeness for usability. Even in cosmology, endurance has a cost. Structures like galaxies persist because they settle into gravitationally stable configurations, but that stability limits their future. A galaxy that remains isolated and undisturbed can endure for trillions of years, but it also becomes dynamically quiet. It stops forming new stars. It stops evolving in interesting ways. Persistence comes at the expense of novelty. This is a theme we've already encountered in earlier pillars. The late universe is not empty, but it is uncreative. Structures persist, but the cost of that persistence is the loss of new structure formation. Endurance replaces transformation. This reframes the idea of success in the universe. Survival is not about reaching a pinnacle. It is about finding a way to remain compatible as gradients fade and options narrow. In many cases, that means becoming simpler, quieter, and less active over time. There is a subtle psychological resistance to this idea. We tend to associate endurance with progress, as if lasting longer means being better in some absolute sense. But in physics, endurance often means giving things up. It means narrowing the space of possible behaviors until only a small, stable core remains. This is why long-lived structures are often boring in a certain sense. They do not do much. They do not change much. They do not surprise us. That is not because they have failed. It is because they have succeeded at persistence. The cost of endurance also explains why transitions are often irreversible. When a system collapses into a simpler, more stable state, it loses access to the pathways that supported more complex behavior. Energy gradients are gone. Correlations are scrambled. The price of stability is that the system cannot easily climb back up into a higher energy configuration. This is not a moral story, it is a physical one. The universe does not punish complexity, it simply does not subsidize it forever. Understanding this helps clarify why the universe looks the way it does at different epochs. Early on, when gradients are strong, complex, active, energy-hungry structures can flourish. Later, when gradients weaken, only structures that can persist cheaply remain. The universe transitions from a world of builders to a world of keepers. This is also why persistence should not be romanticized. Endurance is not a triumph over physics. It is a negotiation with physics. Structures persist by aligning themselves with what physics allows under given conditions. In the next section, we will step back and look at specific case studies across scales. We'll see how the same logic of cost, trade-off, and compatibility appears in stars, galaxies, chemistry, and planetary systems. The details differ, but the filtering principle remains the same. Section 6. Case studies in persistence. Now that we've established the idea that persistence always carries a cost, we can make this framework concrete by walking through specific examples across scales. The goal of this section is not to catalog everything that survives, but to show how the same filtering logic appears again and again, regardless of what the system is made of. Different materials, different forces, different scales, the pattern remains. 1. Stars. Persistence through balance, not strength. A star persists by sitting in a very narrow corridor of balance. Gravity pulls inward. Pressure from nuclear fusion pushes outward. As long as those two influences remain matched within a limited range, the star exists. This is not a robust configuration in the everyday sense. Small changes in mass produce radically different outcomes. Slightly too little mass and fusion never ignites. Slightly too much mass and the star's life ends violently. Even within the allowed range, persistence depends on fuel availability. When fusion pathways change or fuel is exhausted, the balance breaks. What persists longest are not the most dramatic stars, but the most modest ones. Low-mass red dwarfs burn fuel slowly and steadily, remaining stable for trillions of years. Massive stars are spectacular but short-lived. They pay for brightness with brevity. Here, persistence favors restraint. The structures that survive longest are those that operate gently, close to equilibrium, and far from thresholds. 2. Stellar remnants. Persistence through simplicity. When stars die, the systems that remain persist precisely because they no longer do very much. White dwarfs persist because electron degeneracy pressure locks matter into a stable configuration. Neutron stars persist because nuclear forces and quantum pressure reach an extreme but stable arrangement. Black holes persist because, from the outside, they are nearly perfect energy sinks with very few degrees of freedom. In each case, endurance comes from losing complexity, fusion stops, chemistry stops, internal differentiation largely disappears. The object becomes simpler in its macroscopic description. The universe keeps what no longer demands upkeep. This is a recurring lesson. When the environment can no longer support active maintenance, the structures that survive are those that have already settled into configurations requiring almost nothing from their surroundings. 3. Galaxies. Persistence through isolation. Galaxies persist not because they are frozen, but because they reach gravitational configurations that are self-contained. In the early universe, galaxies grow through mergers and inflows. These processes are dynamic and chaotic. Over time, as expansion accelerates and nearby matter is exhausted, galaxies become increasingly isolated. Interactions become rare. Star formation slows. Internal evolution quiets. What persists is not growth, but coherence. A galaxy that survives for trillions of years does so by becoming dynamically boring. It trades interaction for isolation, activity for stability. The cost is the loss of novelty. The reward is endurance. 4. Chemistry. Persistence through energy barriers. Chemical structures persist because reactions are separated by energy barriers. Molecules do not instantly rearrange into lower energy states because doing so requires overcoming activation thresholds. At moderate temperatures and pressures, complex molecules can persist for long times. Lower the temperature too far, and reactions freeze. Raise it too much, and bonds break. Persistent chemistry exists in a Goldilocks zone of energy flow. Outside that zone, structure either cannot form or cannot survive. This explains why chemical complexity flourishes briefly in cosmic history and then fades. As energy sources weaken and environments cool, fewer reaction pathways remain accessible. Chemistry simplifies. Stable end products dominate. Persistence again favors what is hardest to disturb, not what is most intricate. 5. Planetary systems. Persistence through dynamical clearance. Planetary systems persist when they eliminate instability early. Young systems are chaotic. Orbits cross. Collisions occur. Objects are ejected or absorbed. Over time, what remains is a configuration where resonances, spacing, and mass distribution minimize further disruption. A stable planetary system is one that has already lost many possibilities. Planets that could have existed but didn't are part of the cost of the system's endurance. Long-term stability requires narrowing futures. 6. Information structures. Persistence through redundancy or isolation. Information persists either by being copied redundantly or by being physically shielded. Cosmic microwave background fluctuations persist because the universe expanded and cooled before they could be erased. Fossils persist because geological processes locked them away. Records persist when they are duplicated, repaired, or buried. In every case, persistence involves removing information from active interaction. Either you hide it or you constantly fight entropy to preserve it. There is no third option. The universe favors records that require the least intervention. 7. Laws and regularities. Persistence through constraint. Even the patterns we call laws persist because they reflect constraints that remain relevant across conditions. Symmetries endure because breaking them requires specific interactions. Conservation laws endure because they are tied to deep structural invariances. Effective laws persist because they apply broadly, even if imperfectly. What does not persist are descriptions that rely on fine-tuning or narrow conditions. Those dissolve as soon as the environment changes. Again, persistence filters for robustness over elegance. A unifying observation. Across all these examples, a consistent principle emerges. What survives is not what is optimal, but what is compatible. Compatibility means requiring minimal energy input, avoiding thresholds and instabilities, reducing dependence on specific conditions, settling into configurations that resist change. Persistence is not about winning. It is about remaining admissible as the universe evolves. This reframes survival as a passive outcome rather than an active achievement. Systems do not endure because they strive to. They endure because nothing pushes them out of existence. Why this matters. This perspective helps us avoid teleological thinking. The universe is not selecting for meaning, intelligence, or complexity. It is filtering configurations based on whether they can continue under changing constraints. It also prepares us for the next step. If persistence filters structures across scales, then the universe itself can be seen as a long sequence of compatibility tests. Each epoch removes what no longer fits and leaves behind what does. In the next section, we will turn directly to that idea and ask what persistence tells us about selection without intention, how filtering operates without goals, plans, or foresight. Section 7, Selection Without Purpose. At this point in the walk, it becomes important to remove a misunderstanding that almost always creeps in when we talk about survival, persistence, and filtering. The moment we use words like selection, many people instinctively imagine intention, a chooser, a goal, or a preference built into the universe itself. That instinct is understandable. In everyday life, selection usually does involve purpose. Humans select tools, engineers select materials. Organisms appear to be selected for traits that help them survive and reproduce. It feels natural to assume that persistence must imply some kind of hidden aiming, but that assumption does not survive careful examination. In physics and cosmology, selection happens without foresight, without intention, and without any notion of better. What persists is not chosen. It is simply what remains compatible with the conditions that continue to exist. This section is about learning how to think clearly about selection without purpose and why this idea is essential if we want to understand persistence honestly. 1. The core, mistake, confusing outcome, with intent. One of the most persistent conceptual errors in science communication is reading intention backward into outcomes. We see a structure that lasts a long time and conclude it must have been designed to last. We see a system that adapts and conclude it must have been aiming toward adaptation. We see complexity survive and assume complexity was favored. But none of these follow logically. Persistence does not imply planning. Survival does not imply preference. Longevity does not imply importance. A rock persists longer than a tree. That does not mean the universe prefers rocks. A neutron star persists longer than a biosphere. That does not mean life was a failed attempt. Duration is not a measure of value. It is only a measure of compatibility. Selection without purpose means that the universe does not choose survivors. It simply fails to destroy some configurations while destroying others. 2. Filtering is passive, not active. To understand this, it helps to replace the word selection with a more neutral term, filtering. A filter does not seek, it does not evaluate, it does not decide. It allows some things to pass while blocking others, solely based on structure and conditions. Think of a mountain range filtering rainfall. Some slopes collect water, others shed it. The mountains are not trying to direct rivers. They simply shape what paths remain open. The universe works the same way. As conditions change, temperature drops, density spreads, energy sources fade, some structures remain dynamically allowed, while others become unstable. No force targets the unstable ones. They simply fail to persist. Filtering is a consequence of constraints, not an act of choice. 3. Why fitness is a dangerous word in physics. In biology, the word fitness has a precise technical meaning related to reproduction under specific conditions. Even there, it is often misunderstood as strength or superiority. In cosmology and physics, fitness language becomes actively misleading. A star is not fit to survive billions of years. A white dwarf does not outcompete a main sequence star. A black hole does not win against matter. These narratives smuggle in intention where none exists. Persistence in physics has no scoreboard. The only relevant question is, does this configuration remain dynamically allowed as conditions evolve? If yes, it persists. If no, it changes or disappears. Nothing more is required. 4. Why selection without purpose feels uncomfortable. Humans are story-driven creatures. We look for arcs, motivations, and reasons. We expect processes to go somewhere. When we see filtering at work, we instinctively ask, what is it selecting for? The unsettling answer is nothing. Selection without purpose selects against incompatibility, not for meaning. This is difficult to accept because it removes us from the center of the story. It implies that intelligence, life, and observers are not inevitable endpoints, but contingent outcomes that happen to persist for a while under favorable conditions. That does not make them trivial, but it does make them temporary. 5. The difference between local purpose and global neutrality. It is important to draw a clear boundary here. Local systems can have purpose. Living organisms pursue goals. Machines are built for functions. Civilizations plan and adapt. But these purposes exist within the universe, not for the universe. The universe does not inherit the intentions of its contents. A thermostat regulates temperature, but the laws of thermodynamics do not regulate themselves. A living cell maintains structure, but physics does not maintain life as a goal. Purpose is an emergent property of certain systems, not a universal principle. Persistence operates at a deeper, purpose-free level. 6. Why this matters for understanding the long future. If selection had purpose, we might expect the universe to preserve complexity, intelligence, or structure indefinitely. We might expect resets, renewals, or rebounds aimed at restoring what was lost. But because selection is passive, none of that follows. As conditions drift away from those that support complexity, complexity fades. Not because it is rejected, but because it no longer fits. The same filtering logic that allowed complexity to emerge eventually removes it. This is not pessimism. It is symmetry. The universe does not favor beginnings any more than it favors endings. It simply allows what remains dynamically compatible. 7. Persistence is not a goal. It is a constraint outcome. One of the most important conceptual corrections in this entire pillar is this. Persistence is not something systems aim for. Persistence is what remains after incompatible options are removed. This distinction eliminates many false puzzles. Why doesn't the universe restart? Because there is no purpose pushing it to. Why doesn't complexity reemerge at the end? Because the conditions no longer allow it. Why do simple remnants dominate the far future? Because simplicity is cheaper to maintain under weak gradients. None of these require intention. They follow automatically once we stop projecting goals onto physics. 8. The quiet power of this view. Stripped of narrative comfort, selection without purpose can feel cold, but it also offers clarity. It tells us that meaning is not handed down from the universe. It is constructed locally, temporarily, and legitimately by systems capable of caring. It tells us that the universe does not owe us renewal, and therefore does not betray us when renewal ends. It tells us that persistence is not reward, punishment, or destiny. It is the residue left behind by changing constraints. This view is not nihilistic, it is honest. Where this leads next. Now that we've established that persistence filters structures without intention, we can turn to a more difficult question. If selection has no purpose, how do we avoid mistaking endurance for importance? In the next section, we will examine why long-lived structures often feel more fundamental than short-lived ones, and why that intuition can mislead us about what truly matters physically. Section 8. Endurance is not importance. At this point in the walk, we need to slow down and correct a very common misunderstanding about how the universe works. It's a misunderstanding that feels natural, almost unavoidable, because it matches how humans tend to think about time, survival, and meaning. The mistake is this: assuming that whatever lasts the longest must also be the most important. Endurance feels like importance to us. When something survives while other things disappear, we instinctively read that survival as significance. Mountains feel more important than storms because they last longer. Ancient institutions feel more important than short-lived movements. Long-lived objects feel foundational, while brief events feel secondary. When we project that intuition onto the universe, it leads us to a quiet but serious error. We start to think that the far future, dominated by cold matter, stellar remnants, and black holes, represents what the universe was really about all along. We begin to imagine that stars, life, chemistry, and observers were just temporary noise on the way to something more fundamental. But physics does not support that interpretation. Longevity is not a measure of importance. It is a measure of cost. What lasts in the universe is not what matters most. What lasts is what requires the least effort to maintain. Active structures are expensive. A star must constantly burn fuel to remain stable. A living system must continuously move energy, export entropy, and repair itself to avoid decay. A complex system only persists as long as conditions support its upkeep. The moment those conditions weaken, the system does not fail in a moral or philosophical sense. It simply becomes unsustainable. By contrast, a remnant is cheap. A white dwarf, once formed, can persist for trillions of years with no input. A cold rock can drift indefinitely. A black hole, once created, can remain stable for spans of time that dwarf the age of the universe so far. These objects do not last because they are important. They last because they do not need maintenance. This is a critical shift in perspective. The universe does not preserve what is meaningful. It preserves what is stable under low-energy conditions. We can make this clearer with a simple analogy. A fire is dynamic, structured, and transformative. It reshapes matter, releases energy, and creates new chemical states. But a fire requires fuel, oxygen, and gradients. When those disappear, the fire goes out. Ash remains. Ash lasts far longer than fire. But no one would argue that ash was the important part of the process. Cosmic history follows the same pattern. The most significant phases of the universe, star formation, element creation, planetary systems, life, and awareness, are also the most transient. They exist only because strong gradients and energy flows briefly make them possible. When those gradients fade, the universe does not preserve activity. It preserves leftovers. This is why it is dangerous to read meaning backward from endurance. The far future looks quiet, not because quiet things are more important, but because they are cheaper to keep. The same logic applies even at the deepest levels of physics. Fundamental particles persist not because they drive complexity, but because they have no lower energy state to decay into. Space-time persists not because it is the purpose of the universe, but because it is the framework within which everything else occurred. Endurance reflects constraint, not priority. Complexity, by contrast, is always temporary, not because the universe rejects it, but because complexity is costly. It requires separation, flow, coordination, and constant resistance to noise. As the universe expands and gradients weaken, complexity does not lose a battle. It simply runs out of support. This is where emotional confusion often enters the picture. When we imagine a future universe dominated by silent remnants, it can feel as though everything meaningful has been stripped away, as though life and structure were ultimately irrelevant. But that conclusion only follows if we mistake endurance for value. Temporariness does not imply insignificance. A supernova lasts days and reshapes galaxies. A biosphere lasts billions of years and transforms planets. Conscious observers may occupy only a narrow window of cosmic history, but during that window, the universe becomes capable of reflection, memory, and understanding. None of that is diminished by the fact that it does not persist forever. The universe is not ranking its creations. It is not elevating black holes above stars or particles above life. It is simply following the logic of thermodynamics. When energy flows weaken, what remains is what does not need energy to continue. This is why persistence should be understood as a filter, not a judge. It removes what cannot continue under changing conditions. It does not assign importance to what remains. Once we see this clearly, something important settles into place. The quiet, far future of the universe does not negate the richness of its active eras. The fact that complexity fades does not mean it was a mistake. It means it was possible, and possibility itself is not required to last forever to be real. Understanding the universe requires holding both truths at once. Most of cosmic time is quiet. Most of cosmic significance occurs during brief, active intervals. These statements do not contradict each other. They complete each other. The universe does not measure meaning by duration. It measures duration by cost. And with that correction in place, we are ready to move forward. Because once endurance is no longer confused with importance, a deeper question comes into focus. If persistence is a filter rather than a goal, then what kinds of structures survive change well, and which fail not because they are weak, but because they are too rigid? That is where we go next. Section 9. Rigidity, Adaptability, and the Cost of Endurance. Now that we've separated endurance from importance, we can address a deeper and more difficult idea. Survival is not only about how long something lasts, it is about how well something handles change. And not all things that endure do so for the same reasons. Some structures survive because they are rigid. Others survive because they are adaptable. At first glance, both look like persistence, but over long spans of time, they behave very differently. Rigidity feels strong. A rigid structure resists deformation. It holds its shape. It maintains its identity against disturbance. In stable environments, rigidity is an advantage. It allows a system to remain unchanged while everything around it fluctuates. This is why many long-lived structures in the universe are rigid in some sense. Crystal lattices, atomic nuclei, planetary bodies, stellar remnants. They persist because their internal configurations are locked into low-energy states that resist rearrangement. But rigidity has a hidden cost. A rigid structure survives only as long as conditions remain within a narrow range. The moment the environment changes beyond that range, rigidity becomes a liability. A rigid system cannot bend without breaking. It cannot reconfigure without collapsing. It either holds perfectly or fails completely. Adaptability works differently. An adaptable system does not resist change. It absorbs it. It modifies its internal structure in response to external pressure. It gives up local stability to preserve global function. This makes adaptability far more expensive. It requires energy flow, feedback, memory, and active regulation. Adaptable systems are rarely the longest-lived systems in absolute terms, because they depend on conditions that do not last forever. But while those conditions exist, adaptable systems can survive change that rigid systems cannot. This distinction appears everywhere in physics once you start looking for it. Consider stars. A star is not rigid. It is an active, regulated system balancing gravity against pressure from nuclear fusion. That balance allows it to persist for millions or billions of years, but it only works within a narrow range of mass and composition. When conditions change, when fuel runs low or pressure drops, the star cannot adapt indefinitely. It transitions into a remnant. The remnant, by contrast, is rigid. A white dwarf or neutron star has no active regulation. It persists by being locked into a stable configuration. It survives far longer than the star ever did, but it cannot respond meaningfully to change. It endures by refusing to evolve. Both persist, but they persist in fundamentally different ways. The same pattern appears in chemistry. Complex molecules can perform functions, catalyze reactions, and participate in networks, but they are fragile. They break down under heat, radiation, or dilution. Simple molecules, by contrast, persist easily. They drift, collide, and remain chemically inert for vast spans of time. Again, longevity does not align with capability. It aligns with rigidity. Biological systems push adaptability to an extreme. Life survives not by being rigid, but by constantly reorganizing itself. Cells repair damage. Organisms respond to stress. Populations evolve. This adaptability allows life to persist across changing conditions, but only as long as energy flows remain available. When those flows weaken, adaptability becomes impossible, and life disappears long before simpler structures do. This is not a failure of life. It is the price of flexibility. One of the most important lessons here is that adaptability and endurance are often in tension. Systems that are maximally adaptable are rarely maximally long-lived. Systems that are maximally long-lived are rarely adaptable. The universe does not select for one or the other universally. It filters based on context. In early, dynamic environments, adaptability dominates. Systems that can respond to change survive, while rigid ones are destroyed. In late, quiet environments, rigidity dominates. Systems that require no response persist, while adaptable systems fade away. This is why the universe's inventory changes over time. Early epochs are filled with active, responsive structures. Later epochs are filled with inert, stable remnants. The universe is not favoring rigidity. It is moving into conditions where rigidity is the only affordable strategy. This brings us to a subtle but crucial point. Persistence across change does not always mean remaining the same. Sometimes it means changing continuously to remain viable. Other times it means becoming so stable that change no longer matters. Both strategies appear in nature. Neither is better in an absolute sense. Each is suited to a different phase of cosmic history. This helps explain why certain ideas feel paradoxical at first. Life is extraordinarily persistent on Earth, yet fragile on cosmic timescales. Black holes are extraordinarily persistent on cosmic timescales, yet irrelevant to complexity. The difference is not mystery, it is strategy. Adaptability trades duration for function. Rigidity trades function for duration. The universe allows both, but not simultaneously under the same conditions. Another way to see this is to think in terms of bandwidth. Adaptable systems operate across many possible states. They can respond to varied inputs. They can take multiple paths forward. Rigid systems operate in a very narrow state space. They do one thing extremely well: remain unchanged. As conditions tighten, wide bandwidth becomes unaffordable. Only narrow bandwidth systems survive. This is not unique to physics. We see it in engineering, ecosystems, and even institutions. Highly optimized, flexible systems perform extraordinarily well in rich environments, but fail quickly when constraints tighten. Simple, robust systems perform poorly in rich environments, but survive scarcity. The universe behaves the same way. Understanding this reframes how we think about survival. Survival is not about clinging to identity. It is about matching strategy to environment. When environments change slowly and predictably, adaptability thrives. When environments become sparse and static, rigidity wins by default. This also corrects another common misconception. The far future of the universe is not dominated by rigid structures because rigidity is superior. It is dominated by rigid structures because adaptability is no longer affordable. The universe does not choose rigidity, it runs out of alternatives. And that leads us to a deeper insight. Persistence is not a reward, it is a constraint. What survives is what can exist under the remaining conditions, not what once did the most interesting work. This prepares us for the next step in the walk. Because once we understand rigidity and adaptability as strategies rather than virtues, we can ask a sharper question. What happens when conditions change so far that neither adaptability nor rigidity can meaningfully respond? What survives then, and what does survival even mean at that point? That is where we go next. Section 10, Persistence as a Filter, Not a Goal. As we move deeper into this pillar, it becomes important to make one final conceptual correction. We often speak about persistence as if it were something the universe aims for, something systems strive toward, or something rewarded over time. But persistence is not a goal written into the fabric of reality. It is not an outcome the universe prefers. It is simply what remains after conditions have done their work. Persistence is a filter. The universe does not plan. It does not evaluate. It does not select with foresight. It changes conditions, and those conditions quietly remove whatever cannot continue. What remains afterward can give the illusion of being favored, but that illusion dissolves once we understand how filtering works. To see this clearly, it helps to imagine a landscape that is slowly changing shape. As the terrain shifts, some paths become impassable, some structures collapse, and others remain standing. The structures that remain did not win. They were simply compatible with the new shape of the ground. Persistence emerges from compatibility, not intention. This distinction matters because it prevents us from reading purpose where there is none. When we see that certain particles persist while stars die, or that black holes outlast galaxies, it is tempting to think the universe is converging on some final preferred state. But physics does not support that narrative. The universe is not converging toward anything, it is relaxing. Every time conditions change, a filter is applied. Structures that depend on narrow ranges of temperature, density, or energy flow are removed. Structures that require constant maintenance disappear. Structures that can exist passively remain. Over time, the filters become stricter, not because the universe demands it, but because gradients weaken and options narrow. In early epochs, the filter is permissive. Many structures can exist at once. Stars form, galaxies assemble, chemistry flourishes, complexity rises. The universe explores a wide range of configurations because energy is abundant and contrast is strong. Filtering is gentle. As time passes, the filter tightens. Expansion dilutes matter. Energy spreads out. Interactions become rarer. Structures that once could be maintained no longer can. The universe does not remove them violently. It simply stops supporting them. persistence becomes harder, not because something opposes complexity, but because the environment no longer subsidizes it. This is why persistence should never be confused with success. What persists at one stage of cosmic history may be irrelevant or impossible at another. Persistence is always conditional. It reflects the current state of the environment, not a universal hierarchy. This perspective also explains why the universe looks so different at different times. The early universe is a place of rapid change, structure formation, and energetic activity. The late universe is a place of stability, inertia, and quiet endurance. These are not two universes with different rules. They are the same universe passing through different filters. The filters themselves are not arbitrary. They arise from thermodynamics, expansion, and geometry. As gradients flatten, fewer processes remain possible. As distances grow, coordination breaks down. As energy becomes dilute, maintenance becomes impossible. Each of these changes removes entire classes of structure without targeting any specific one. Seen this way, the future dominance of inert remnants is not a conclusion the universe is heading toward. It is a residue left behind by filtering. This framing helps dissolve another deeply rooted misunderstanding: the idea that what remains at the end must somehow explain everything that came before. In reality, what remains often explains very little about the active phases that produced it. Ash does not explain fire. A fossil does not explain life. A black hole does not explain the galaxy that formed it. Remnants are records, not purposes. The universe does not preserve what explains it. It preserves what cannot be removed under the remaining conditions. This is especially important when we think about meaning. Humans are prone to asking what the universe is for, or what it is building toward. But filtering does not imply direction. A sieve does not know what it keeps. It only knows what it removes. Once this is understood, many apparent paradoxes fall away. The disappearance of life is not a verdict on life. The persistence of particles is not a statement about their importance. The quiet far future is not a correction of a noisy past. It is simply what remains after filtering has done its work. This also clarifies why persistence does not guarantee relevance. A structure can persist long after it has ceased to matter in any functional sense. A cooled remnant still exists, but it no longer participates in shaping the universe in meaningful ways. Persistence preserves existence, not influence. At the same time, this framing prevents despair. If persistence were a goal, then everything temporary would feel like failure. But if persistence is merely a filter, then temporary structures can be understood as fully legitimate expressions of what the universe can do under certain conditions. They were not mistakes, they were possibilities. This includes life, consciousness, culture, and understanding itself. These phenomena arise when conditions allow them and fade when conditions no longer support them. Their impermanence does not diminish their reality. It defines their context. The universe does not regret losing them, and it does not celebrate keeping remnants. It simply continues. There is also a quiet humility in this view. It reminds us that nothing persists because it deserves to. Persistence is not moral. It is physical. What survives does so because it fits within the narrowing constraints of time, energy, and space. This brings us to a final realization for this pillar. Asking what survives is not the same as asking what matters. The universe answers the first question without caring about the second. Meaning is not filtered the same way matter is, and that leads naturally to the closing of this walk. If persistence is a filter rather than a goal, then understanding the universe is not about identifying what lasts forever. It is about understanding what was possible when it was possible, and why those possibilities eventually closed. That is not a story of loss. It is a story of structure moving through conditions. In the final section, we will step back and bring all of this together. We will talk about what it means to take this long view seriously, why patience is essential to understanding the universe, and why a picture that includes everything, even what fades, is more complete than one that only celebrates what endures. Section 11, Closing. What it means to take the long view. As we come to the close of this pillar, it's important to slow down rather than rush toward a conclusion. This was never meant to be a story with a sharp ending or a single takeaway. It was meant to be a long walk through an idea that only makes sense when you give it time. What survives when conditions change is not a simple list of objects or laws. It is a pattern of filtering, shaped quietly by constraints, costs, and compatibility with the environment. Throughout this walk, we've seen that persistence is not a reward and not a goal. It is not something the universe strives toward or values. It is what remains when conditions have finished removing what they no longer support. Some structures last because they are rigid and cheap to maintain. Others persist for a time because they are adaptable and actively regulated. Still others appear briefly, do extraordinary work, and then vanish when the gradients that made them possible fade away. None of these outcomes are judgments, they are consequences. One of the hardest things to accept, especially from a human perspective, is that importance and endurance are not the same thing. The universe does not preserve what is meaningful. It preserves what is stable under the remaining conditions. Meaning arises locally, temporarily, and contextually during periods when energy flows, contrasts, and interactions are rich enough to support it. This is not a bleak realization, it is a clarifying one. When we stop expecting the universe to justify itself through permanence, we free ourselves from the idea that what fades must have been pointless. Stars do not need to last forever to matter. Life does not need to persist indefinitely to be real. Understanding does not need to survive the universe to be worth achieving. The universe is not a machine designed to produce a final state. It is a process unfolding through changing conditions. At different moments, different kinds of structure are possible. When those moments pass, the structures pass with them, not because they failed, but because the window closed. This pillar has also been about patience, not patience as a moral virtue, but patience as a physical necessity. Many of the most important truths about the universe only become visible when we stop focusing on dramatic events and start paying attention to long, quiet processes. Filtering happens slowly. Adaptation happens gradually. Endurance reveals itself over timescales that resist narrative. If we rush, we miss what is actually happening. Taking the long view does not mean abandoning curiosity or surrendering to stillness. It means learning to see structure where nothing appears to be happening. It means recognizing that stability is not emptiness, and quiet is not absence. It means understanding that most of the universe's history is not spent building or collapsing, but persisting. There is also something deeply inclusive about this way of seeing. When persistence is understood as a filter rather than a goal, there is room for everything in the story. Short-lived systems are not mistakes. Long-lived remnants are not the punchline. Early complexity and late quiet both belong. Nothing needs to be erased from the picture to make it coherent. That matters because the universe itself does not erase its past. It carries it forward in structure, in remnants, in correlations, and in constraints. Even when information becomes inaccessible, it is not annihilated. It is dispersed. Even when activity fades, existence continues. This perspective also reshapes how we think about ourselves. We are not central to the universe, but neither are we incidental. We are part of a phase in which the universe is capable of reflection. That phase may be brief on cosmic timescales, but it is real, and it is rare. The fact that it does not persist forever does not make it less meaningful. It makes it precise. Understanding what survives when conditions change is not about predicting a final answer. It is about learning how to ask better questions. Instead of asking what lasts forever, we ask what is possible now and why. Instead of asking what the universe is for, we ask how it behaves when constraints shift. Instead of searching for intention, we study structure. This is the quiet discipline that runs through everything we've discussed. If you've stayed with this pillar, that patience matters. It mirrors something true about the universe itself. Most of its work is done slowly, without spectacle, without announcement. Most of its filtering happens in silence. To understand it, we have to be willing to slow down as well. This was not a story about survival in the sense of triumph. It was a story about endurance, adaptability, rigidity, and cost. It was a story about how reality keeps going without aiming, without memory of its past goals, and without concern for narrative closure. Thank you for being here, and thank you for taking the time to walk through this carefully. This has been part of the Persistence Information Weave, exploring how structure survives, adapts, or fades as conditions change. If you'd like to continue, you're welcome to join me in the next pillar, where we'll turn to a different set of questions and a different scale of structure. Each pillar stands on its own, but together they form a wider picture. Who knows where science will take us by the next video?